Hello everyone, welcome to the Rust programming language tutorial series. This is the next lecture. So if you haven't watched the previous lectures, please go ahead and watch the tutorial videos and then come back to it because it is a continuation. Today, we are going to talk about memory management in Rust. Okay, how Rust manages memory, where are the variables stored, those concepts we are going to talk about. Now, Rust programs memories live in two areas. Either it lives in stack area of the memory or it lives into heap. We'll see how each one is different. Variables, when you first define them, or rather if you define them the way it is shown in here in this particular program here, this snippet, they are stored in a memory area called stack. So see, for example, here you're defining in the main n is equal to 5. So when the program is at this line 1, see this area stack, and now here you have to see that this is the frame for main, right? This is the main method, the method name main, right? So it defines n is equal to 5, so this is one frame. Then when it comes to line 3, L3, what it is doing is it's calling +1, okay? Or rather, when it calls +1, second line, this is executed, okay? It calls a function +1. So what it does is, see, in the same memory area called stack, it'll create a new frame. And now what you have done is done x +1. So first, you're returning x +1. But here what you're doing is the value that you're passing to x is 5 because you're passing n here. So what it does is it creates allocates a new memory area for this +1 function, names it at x, and stores the value 5 in it. And then when this function returns, it goes out of scope. So when it comes here, the function is executed. And so when this line is executed, let y be equal to this. So y is equal to whatever +1 returned. So x +1, 6. So here 6. Again, just a reminder from the previous lecture, just see that there is no semicolon here. So if you have to return value, the statement does not have a semicolon in the end. Whereas the other statements, they do have a semicolon. So once this is executed, see here, this is how the final stack looks like. N, which is still in the scope, remains. Y is still in the scope, remains. But the memory that was allocated for +1 is deallocated. Now this deallocation, Rust does on its own. Like we don't have to call the any method to free the memory area. Rust deallocates the function frame once its execution is over or it goes out of scope. Variables here. So when an expression reads a variable, the variable value is copied from its slot into the stack frame. So say for example, first, this is a similar line, L equal to 1, inside function main. So it will allocate a memory area, name it as A, store the value 5 in it. Then this line comes, see, it's copying, right? But it's a mutable B. So what it will do is create another frame, allocate another area in the memory, name it as B, and store the value 5 in it, okay? And then when B plus equal to 1 is called, this changes here, but the original A equal to 5 remains. So this is like variables are, the values are copied, not the references. Now, to transfer data without copying, so see in the previous example that we saw that it was copied, right? We had A equal to 5 and then mutable B equal to whatever, B equal to A. So what it did was it copied. But when you have huge values, like here, 1 million, right? In that case, if you make a duplicate copy, you're wasting stack memory, right? Or unnecessarily, you are using the memory when you don't have to for large variables. In order to solve that, Rust provides something called as heap area. Okay, and Rust also has a concept of pointers. So a pointer, what is a pointer? It's a value that describes a location in the memory. So you see here, A. Now what does A have? It does not have value, any value. It has a memory A. Of course, it will have a value, but that value will be nothing but the address, memory address, where the value of A is stored. The memory address in another memory area, which is called as heap. So see, this is stack, this is heap. So what will the pointer here have? The name of the pointer is A. Its value is the memory address where the value is stored. It's actually the physical address. It would be something like OX, something, the memory address in hex. Now notice what happens when you execute line 2. Let B equal to A. A goes out of scope, so Rust will claim this memory back. You will no longer be able to access A, and now you will have a new memory, a new variable called B, which is pointing to the same memory location. So what value this will have? It will have the same address that was here, the address of the same memory location. Okay. So when a variable owns a box, so this is a box, how do you create or rather, how do you create a variable inside a heap and create a pointer? You use box.new. Okay? So Rust provides a construct called box for putting data on the heap. So here, see, it's for example, we can wrap the million element array in box new. All right. So if a variable owns a box, when Rust deallocates the variable frame, it also deallocates the box's heap memory. So if both A and B are out of scope, this area will also be freed automatically by Rust because they both were pointing to this. So Rust takes care of freeing up unused memory area on its own, whether it's in a stack or it's in a heap. So see, look here, this is a very interesting example here. So if you see, what you're doing is you're creating a variable called first. It's a string variable from Ferris. Okay, that's line 1. You call full. Next expression, you call the method add suffix, and you pass the first. First, the location of the memory address is passed. What it does is nothing but in the string, it calls the push string method, adds junior to it, and returns the name. And the name is allocated here. Now let's see what happens behind the scenes in the memory. So when you allocate using this way, like string from Ferris, it will create a variable or a pointer named first. It is supposed to have a value. Now, since you're using this construct, okay, so it's not only box, but if you're using like something, these construct like string and all, it will also be stored in the heap memory area. And what you have assigned it with? Ferries. So it will have the ferries, and the pointer will have the address of this memory location. Okay. Now, next up, what you do, you pass this first to this function called add suffix. And add suffix is referencing it by the variable name. So what happens is in L2, when the method is called, first goes out of scope. Rust creates another variable. Its name is name, and it points to the same memory address. Line 3, still its name, what happens? It pushes junior. So see here, updates this because this is mutable. You can update the value. It goes in here. Now it returns the name, right? See, name is the return value. There is no semicolon, and it assigns to full. So now first is gone out of scope. Add suffix and name is gone out of scope. So if you look here on line 4, after the method execution, Rust has deallocated the memory that it had allocated for add suffix function. This variable, after it returns, it's assigned to full. So name and first, everything is gone. And you have now full pointing to the updated string. So this is very important. Just take a look at it one more time. Go through this. How Rust allocated the memory. When you pass the variable to a function, creates a new frame in the stack. Once the function is returned value, it goes out of scope. Rust deallocates the memory. And in the end, only the current variable is left. All the other memory areas are claimed. So this is a very, very, very important concept. So this was all for today. Follow it properly because in the coming lectures, we are going to learn more about advanced memory management. Okay, boxing, referencing, many concepts about memory management in Rust. All right. You can copy this program and run it again if you have downloaded the Rust compiler. Download it, run the program, but you won't be able to see the memory area, but still you'll see how the program runs. Okay. All right. Thank you all for listening. See you all again in the next lecture. Thank you.